So our next speaker is Professor Jeff Gray. And as saying, Professor Gray has been a researcher in photovoltaics for a long time.
Not as long as you. Well, no, maybe the same. Okay.
Probably, yeah. You were here when I came.
That's true.
Yeah. So he's an old timer, but he's worked on a lot of different solar cell technologies, primarily in modeling and simulation. The results that I showed you in my talk, all of these lines and plots about where the recombination was occurring, that all came from his simulation tool. So Jeff is going to talk to us, I guess, about simulation and simulation more generally, and about something about what goes on inside the simulation program.
Yeah, a little bit, yeah.
Okay.
All right, thank you, Mark. So can everyone see the mouse pointer? Okay, because I'm going to use that rather than the laser so I can see better what's going on. All right, so first I'll just go over what I plan to talk about this afternoon. So I'm going to talk about, so when we're doing modeling and simulation, why we're doing it. Then I'll talk a little bit about single junction or just PV device modeling, just the device itself. I'll talk a little bit about fundamental limits. Then I'm going to talk a little bit about system modeling, and that's something that I've gotten into relatively recently. And then I'll talk about detailed numerical simulation, and those are the results. That's basically what Professor Lundstrom was referring to when he was talking about the plots and stuff that he generated. That came from a detailed numerical simulator, Adept. And I'll try to give you just a kind of quick overview of what's under the hood of a simulation program like Adept. And it'll be pretty much universal in terms of whatever simulation program you might be using. You have some basic idea of what's going on and what to believe and what not to believe when you see your results. All right, so objectives of PV modeling and simulation. And a lot of times you'll hear modeling and simulation, the term modeling and simulation used interchangeably. Really what I'd like to try to think about it more as we have models, so we create models, and that's the modeling part. The simulation is when we apply those models to either analyze a device or a system or make predictions about what's going to happen. So we use the models and the simulations for two main purposes, at least from one perspective. And one is to sort of understand what's going on with the terminal characteristics. And I think Professor Lundstrom went over the solar cell figures of merits with you of open circuit voltage, short circuit current, fill factor, efficiency. And we'd like to, okay, how does the device design or the device structure, how are those choices affect those figures of merit? And things that go into that are the size and dimensions of the device, thickness of the layers, the doping of the emitter compared to the doping in the base layer, whether we put window layers on it or not, all sorts of things like that. Plus it also, in terms of the choice of materials, and there's the material parameters, mobility, lifetimes, etc. And some of those, things like lifetime in particular, you can have a device or a material that's identical in every respect except for its lifetime, and that tends to be more of a process type things. So some things are fundamental properties of materials, and other things are process properties of materials where if you refine your process, you can see some improvements in performance of solar cells or other devices. And then what you really would like to do then once you have that is think you have a good model, use the model to make some predictions, either by say, well, if I change this, how will the performance improve or change? Or if you're testing in the laboratory at 25 degrees Celsius and you take it, solar cell out into the wild and put it under the sun, it's going to heat up significantly, from 20 Celsius to 40 or even more Celsius, and how is its performance going to be under those conditions? And so those are all sorts of things that modeling and simulation can be used for. And hopefully the use of the modeling and the simulation will lead to improved designs. So I'm going to talk about some various levels of modeling, and we'll sort of end up with the detailed numerical modeling. But simpler models have a lot of use too, and so I'm going to talk. So compact models are basically things that are based on the terminal characteristics that may be more empirical in form. They'll be based on some fundamental physics like the Shockley diode equation, which is what I'm going to show here in a second. But they'll give you some idea of what's going on. So that, they'll use lump circuit elements and maybe semi-analytical models, which we'll see here in the next slide. And so a fairly common representation of a solar cell is what I've shown here. The sun is represented by this current source. There's two junctions, or it looks like it's a two diode model in this particular case. One diode is sort of representing, the diode labeled 1 is sort of representing the bulk behavior of the device. So I think when Professor Lundstrom hopefully talked to you about quasi-neutral regions and depletion regions in the device, so the diode 1 is going to sort of reflect the behavior of the quasi-neutral region of the device, and diode 2 is going to reflect the behavior in the depletion region of the device. And then there's some parasitics that get attached to that. And here we're just talking about steady state, so there's no capacitances here. But if you're doing this under time-varying conditions, then you would also include some capacitors. And there's a shunt resistor, which is basically a leakage maybe around the edge of the device. Would be one way you could get some shunt. And then series resistance, and series resistance typically comes from the sheet resistance of the emitter layer, because you have a front grid, which you'll see here in a minute, where the current has to flow laterally, and that gives you some resistive losses. The grid fingers themselves, the metallic grid that you attach to make electrical contact will also add some series resistance. And so it's very common to use a model of this form to basically be able to predict what the IV characteristic looks like. So we just take a look at all the terms. Corresponds to the short circuit current is the current source. This term is diode number 1. The second term is diode number 2. And there's a shunt resistor here and a series resistance there. And you can see that the voltage across the junction is not the same as the terminal voltage, and that's why the series resistance appears in the exponentials of basically the Shockley diode equation. I01 and I02 are sort of fundamental parameters of the material that the diode is made of and of the recombination processes involved. I01 is typically a much smaller number than I02. But it doesn't necessarily have to be that way. Okay, so then we move on to analytic models, and those are based, on the relevant device physics, simplified though, and typically minority carrier diffusion equation. And I'm guessing that Professor Lundstrom talked, or one of the lecturers talked about the minority carrier diffusion equation. We're going to talk about it some more today. So if you're not sure what I'm talking about, we'll see that again later. And the analytic models provide a little bit deeper insight into the device operation and design dependencies. Much better than a lump system, a compact model, where you have to make some inferences to lumped resistors and very gross sort of things. You can look a little more carefully at things with an analytic model. The device and material characterization, a lot of device and material characterization methods are based on these models. But they are limited. In order to be able to basically get a closed form solution to the minority carrier diffusion equation, you have to make quite a lot of simplifying assumptions. So we're going to talk, like I said, we'll talk about the minority carrier diffusion equation here for a moment. And let me talk a little bit about my notation in the equation right here. So the little m's are referring to the minority carriers. So if this was and the capital M is referring to the majority carrier. So if we were in a p-type region, let's say over here in this p-type base region, M would be a capital P, and the minority carrier is electrons, the M would become a little n. But it's the same equation otherwise between the two. And a simple way to apply the minority carrier diffusion equation is to solve it in these regions independently. So we would solve the minority carrier diffusion equation in the emitter region here. And a couple of minutes ago, I had mentioned that current flow you'd see some lateral current flow. And actually let me just digress a moment to talk about that. You're going to have current flowing out of the P side of the device. And so current will be flowing in this direction. The black here represents the contact, so the current will flow in through the contact, and then it'll spread out laterally and flow pretty much uniformly, especially by the time it gets to the base region as it exits the base contact. So this emitter region right here is a source of the series resistance. So let me get back to that. So everyone here, I'm sure, has had differential equations, and you have differential equations. You need a region in which you're going to solve that differential equation, and you need two boundary conditions. So here we actually have three different regions. We can only apply the minority carrier diffusion equation to two of them, the so-called quasi-neutral regions. So here's the N+ region emitter. We'll assume it's quasi-neutral, and we'll also assume the base is quasi-neutral. And for the sake of this discussion, we're going to assume that the depletion region isn't really adding anything to the device. So there's very little recombination or generation going on in the depletion region. And in good solar cells, especially operating at a sufficiently high illumination level or forward bias condition, you can pretty much ignore what's going on in the emitter. Let's say in a good silicon solar cell, the diode characteristic is typically an N factor equals 1, which is your hint that you don't really have to worry about the depletion region very much. You can include it, but you don't use a minority carrier diffusion equation to account for the current generated in the depletion region. And for the sake of this discussion, we're basically going to assume that generation and recombination are 0 in the depletion region, so that all the current and recombination that we see are going to be in the emitter and in the base. So I need two boundary conditions. At the edge of the depletion regions, we're going to apply the law of the junction, and I believe I saw in Mark's presentation a discussion of the law of the junction, so I'm not going to belabor that point. But that gives us a boundary condition that depends on the junction voltage. And then at the back contacts, we also have boundary conditions. And at the front contact, we use a surface recombination boundary condition and SS effective. And the reason it's SS effective is because there's actually, even though you can do two-dimensional, even three-dimensional simulations, if you're going to solve the minority carrier diffusion equation, though, for the most part, if you're going to get an analytic solution, you're going to limit yourself to one dimension. So you have to basically treat this surface as a single point and come up with a single boundary condition that will account for what's going on at that interface. And right here, I was just illustrating that with S sub S effective. So this is an effective front surface recombination velocity. At the back contact, you'll see I have two different boundary conditions. If this back surface field here, or this P+ region here wasn't there at all, we would use this boundary condition, which basically means that it's a perfect ohmic contact, and the excess carrier concentration at the contact is identically equal to 0. And if you took a simple device physics, in your very first thing you looked at in a device physics course, solving the minority carrier diffusion equation, that's probably the assumption that you made. However, in a good solar cell, you're going to put a more heavily doped region here at the back to basically prevent the minority carriers from reaching the contact, because recombination is bad, and hopefully we'll see some illustrations of that later. And in that case, there would be a back surface recombination velocity that we would use to represent that. And I'm going to show some slides that will show how the predicted performance of a solar cell is going to depend on some of these parameters to give you a little bit better intuitive understanding. Okay, so it's worth noting, like I already mentioned, that the front surface recombination velocity is not just a single, from a single, it's not just from the contact, and it's not just from the passivated surface here, which is this is where we let the light in. It's actually a combination of the two. And you can derive a fairly simple, I mean, it doesn't look that simple, but it really is a fairly simple expression for what that effective front surface recombination velocity is. And I'm not going to go through all the terms here right now, other than just to point out a few key ones. This little small s here represents the percentage of front contact coverage. So that's basically the area of this small finger right here compared to the total area, surface area of the device. Because that'll end up being a key parameter. G is sort of the average generation rate in the emitter. And you probably recognize all the other terms. You see the diffusion length and the thickness of the device and as such in there. So it's hard to look at this and really understand what's going on, but you can look at a few special cases just to get a feel for what's going on. So let's suppose that you were able to make the grid size so small that it was essentially negligible, or getting very close to zero. Then the front surface, effective front surface recombination velocity would just be whatever characteristic velocity of the surface of in this case, silicon of the semiconductor with its anti-reflective coating. And typically you can get those numbers down quite small, as low as 1 or 2, I think, in some of the best silicon solar cells, maybe even lower than that now. If you have full metal coverage, the effective surface recombination velocity goes to infinity, and that's equivalent to, go back here, to saying that the excess carrier concentration goes to 0. In fact, if you look at this equation, this goes to infinity. The only way to keep the derivative finite is for the excess carrier concentration here to go to 0. So infinite surface recombination velocity basically corresponds to an ideal ohmic contact. In the dark, you get effective surface recombination velocity that's some function of the coverage of the device. It'll be the actual one plus a term depending on the diffusion coefficient and the thickness of in this case, the emitter layer. At short circuit, in terms of the modeling, effectively when you're at short circuit, assuming there's no series resistance anyway, it's as if the metal contact isn't even there. What you would model it with would be whatever the free surface of the semiconductor were to look like. But at open circuit voltage, it would be a different number, which would be a combination of whatever that free surface looked like. And basically this term here is sort of the effect of the metal on it, on the surface recombination velocity. What we found when we did simulations is that you're pretty well off, even though you're not going to be right at short circuit exactly. Recombination at short circuit in a good solar cell really isn't typically all that important. And if you model it with whatever it should be near open circuit voltage, you'll do a pretty good job. So you don't really need to use your analytic model with a lot of different values and trying to figure out. You can say, well, this is characteristic of the front surface, and that's what you'll use. But I digressed a little bit here, so we'll go back to the minority carrier diffusion equation. And just not worry about SF effective, how it varies. We'll just treat it as a constant when we look at the solution to it. So, and we can learn a lot by solving the minority carrier diffusion equation. And I'm not going to do a lot with it other than just show you the basic scheme for solving it. Anyone who took in their first differential equations course, this is the second order differential equation. With the forcing function, which is the generation rate. You basically take the homogeneous solution, add a particular solution, invoke the boundary conditions, and solve for basically all of these coefficients. And we're not going to take the time to do that, and I'm sure everyone breathes a sigh of relief not to have to go through and derive this, but if you want to, you can certainly do that on your own. It's tedious, but it's very straightforward. In fact, you don't even have to really know differential equations, because once you recognize what the solution is, it just becomes a messy algebraic equation. Okay, so we're going to assume that we've solved for all the coefficients, and now we can actually look at a lot of things. So we can for instance, we could plot the minority carrier concentration if we wanted to. I'm not going to show that here, but we can basically from this derive the terminal characteristics and see how the terminal characteristics depend on some key parameters. And that's what I'm going to show you here in the next few slides. So if we take sort of a typical silicon solar cell, this is going to be results for a typical silicon solar cell with nominal choices of parameters, and I'm just going to vary a few of them. So what I'll vary in this particular case is everything else will be the same, but I'm just going to vary the base lifetime. And the surface recombination velocities will be sort of nominal ones. I'll vary those later so you can see what the dependence of those kind of things are. But if you look at base lifetime, and this is most solar cells are going to be dominated what's going on in the base. You know, the emitter does add some effects to it, but the primary, the first order behavior of the device is going to be dominated what's going on in the base. So I'm going to focus on those parameters here. And this dashed line down the middle here is representing the point at which the diffusion length is either is equal to the thickness of the base. And those of you who have taken a device physics course probably remember there's a short base diode approximation and a long base diode approximation. So when you're on this side of the curve, especially, so that this ratio is about a third of the thickness of the device, you would call that a long base diode because the diffusion length is much smaller than the thickness of the device. And over here, once you have the diffusion length 2 or 3 times the thickness of the device, that would be considered a short base diode. So there's sort of 2 regimes of behavior that you can see here. And as you might expect, if you think about it, a long diffusion length corresponds to a long lifetime. And so you have relatively little recombination going on. And therefore, if you have little recombination, the open circuit voltage should be higher. You should get higher short circuit current. And basically, because the open circuit voltage is going up, fill factor also goes up. And we'll see that a little bit, the relationship between open circuit voltage and fill factor later on. But really the 2 key ones then are really the open circuit or short circuit current behavior here and open circuit voltage behavior here. And as you might say, as you might well guess, the better your lifetime, the better those figures of merit are. Now in this particular case, we picked a nominal base lifetime, and I don't quite remember what it is, but it's going to be in the short base diode approximation, which means it would be a good solar cell. And this is showing what the effect of the back surface field is. So this is you can see that with or without a back surface field, what the behavior would be. So basically, a perfect back surface field would be over here with essentially a surface recombination velocity of 0, which means there's no flow of minority carriers to the back contact, instead they're basically being able to be collected. And add to the output of the device. And over here, basically 10 to the 7th that's the thermal velocity, and that's essentially equivalent to being infinite surface recombination velocity. And this particular curve would tell you how well you would have to be able to do to get effectively, what the S would have to be an effective barrier to the minority carriers. And then you could tie that to, in this particular case, a doping level for the back surface field to see how close you can get to the ideal case. But clearly there's a lot of improvement that you can gain by having a back surface field. The short circuit current can drop by, that's like, 3 parts out of 36, so it's almost a 10% effect on the short circuit current. And you can also see it's a significant effect on the open circuit voltage over here. Okay, another thing that's useful to look at when you're looking at a solar cell is the spectral response, which is basically looking at what the short circuit current is as a function of monochromatic light. So if you think about absorption, high energy photons are going to be absorbed more quickly than low energy photons are. And so if you which means that the front surface is going to have much more of an effect on the collection of high energy photons than it would have on the lower energy photons. And you can kind of see that in this particular expression. So the solid line is, I guess I don't have it labeled, but I believe it's a number right around 1,000 or so for the front surface recombination velocity. And if you increase that even more, basically, which you can see, it's in terms of the high energy photons. Even when you increase the back this is with the back surface on here. So it's not doing very good with the high energy photons. But if you were able to passivate that front surface and get the front surface recombination velocity, in this case down to 100 centimeters per second, then you basically get a flat response out of this. And this also shows the effect of the back surface field on the spectral response. And what this is showing is that the longer wavelength or lower energy photons are better collected when the back surface field is reasonably good. Back surface field of 10 to the 7th, is, like I said, is basically like having no back surface field. So you don't have a back surface field at all. And your red response, which is the longer wavelength photons, they get absorbed back there, and because they're right next to a contact, they recombine immediately and can't be collected by the junction. But if you put a back surface field on, as in this case, and I don't remember exactly what number I used here, but let's assume it's 0 just for the sake of argument, then you got a good chance of collecting many of those photons. Much better chance than you would if there was no back surface field there at all. So this gives you some insight into why you might want to change the design of the device in such a way so that you can improve these things. All right, so that kind of gives you a general sense of what's going on with how a model might be used. So what I'm going to try to do right now is basically use some very general modeling let's just take a look at what makes a good solar cell and see if we can come up with maybe some general design rules for a good solar cell, just based on some very simple modeling considerations. And I know for a fact that Professor Lundstrom showed you an equation much like this, and this particular one, but maybe I better go up here. So first, the key thing is always open circuit voltage. If you're making a solar cell, you're going to be able to probably get a good short circuit current relatively easily. Unfortunately, you're not even halfway there once you have a good short circuit current. And I think Professor Alam here, yeah, he's sitting there in the back, and he knows that from his organic solar cells. They probably have much better short circuit current than they do open circuit voltage. And it's much easier to get the short circuit current, but at open circuit voltage, that's basically where all the warts show up. So, a good solar cell, if you can get a good open circuit voltage, you probably have everything else handled in the device as well. It's not 100% sure, but very good case for that. So in this particular example, that's what I'm going to assume, is that we're going to look at the open circuit voltage, and then we're going to consider a solar cell which has that perfect back surface field. So minority carriers will not combine at the back contact. They have the best chance possible of being collected or contributing to the open circuit voltage. And a very thin emitter, so again, we have almost no recombination going on at the front surface. And so a very good emitter not only includes having a very thin emitter, but that implies something about the front surface too, because that's connected to the emitter. So we're going to assume that we have somehow made a perfect back surface reflector and have an emitter that basically contributes nothing to the recombination. Now, those are hard things to accomplish, but in this particular, we're going to try to look to see where we could get with things. And so let's assume that we were there. And then all that's left then to consider is the base region of the device. So, so that at open circuit, the minority carrier in the base is going to be constant with position. So, and the way to think about that is that, okay, at open circuit, there's no current flowing. And the current flow, remember, is the gradient of the carrier concentration. So if the current is 0, that means that the gradient is 0. And I set a boundary condition at each side. One is that the short circuit current is 0, and one is that there's no minority carrier current, no minority carrier current at the back of the device. So the excess carrier concentration is going to be exactly constant, which means that when I perform this integral, it's very easy because R is constant, G is, and I'm going to assume G is constant, even though it really isn't, but it's very easy to treat it that way. And we'll talk a little bit more about that when we look at the result. But I'm going to assume that I guess here I don't even really have to, because I'm just saying the integral of the generation rate is the light generated current. And I guess even if you have an exponential relationship there, you can integrate that relatively easily. But this is the key part right here. So you have the minority carrier density divided by the lifetime, which is basically the recombination rate, times the thickness of the base, times Q to get current. And that should be equal to, has to be equal to the light generated current. Now we'll go back and look at the law of the junction because we want to relate this to a voltage. So we take the minority carrier current and calculate an equivalent open circuit voltage, or minority carrier concentration, and calculate an equivalent open circuit voltage. And with this from the previous page, just a little bit of algebraic manipulation will give us that the open circuit voltage is KT, and there should be, I'm probably missing a Q, but it's not a big deal. And this should be Q, this should be KT over Q, sorry. Natural log of the doping in the base, lifetime in the base, the light current divided by the charge, and the intrinsic carrier concentration squared and divided by the thickness of the base. So that's the open circuit voltage. And just for completeness, you really need the other figures of merit here also. And we're going to assume that you're basically any light that's created in the device you're going to be able to collect. And that's really a pretty good assumption. It's very easy to get very close to 100% of the photons collected or generated actually collected. With at least within 1 or 2%, and maybe even closer to that. Fill factor expression here, this is actually, quite exact. You can actually calculate the fill factor exactly. It turns out to be a transcendental equation. And I thought about deriving that for you today, but that would have taken the rest of the time probably to do that. You can check out this reference, and he talks about how that comes up. But this is quite good all the way down for band gas, down to about 0.2 of a volt. So for all intents and purposes, this form for the fill factor, ignoring series resistance anyway, is quite exact. And so with the open circuit voltage, short circuit current, and fill factor, you can calculate the efficiency of the device. But like I said, we're going to focus here on the open circuit voltage because that'll be the key thing. One thing you can maybe not see obviously here, but it's true, is that the higher the open circuit voltage, the higher the fill factor. So increasing the open circuit voltage is always good. And in this case, we're assuming that we're getting all the short circuit current is basically just constant. So improving the open circuit voltage will automatically improve the fill factor. And then that in combination will automatically improve the efficiency, which is obviously our ultimate goal. But we've broken it down to the key parameter, which is the open circuit voltage. So let's take a look at this and say, so high open circuit voltage yields a high fill factor and a high short circuit current, and therefore high efficiency, and repeated the open circuit voltage equation here. So let's just take a quick look at this. So JL is basically, is going to be, ideally it would be the number of photons in the solar spectrum whose energy is at or above the band gap of the semiconductor. Now it's hard to do that because as you get close to the band edge, the absorption isn't perfect. You can't have an infinitely thick semiconductor, and so some of the photons are going to pass right through the semiconductor without ever being absorbed. But you can get close to that, and there's some tricks you can pull It's called light trapping. So you, like, for instance, if you texturize the front surface, in other words, instead of the light coming straight in, it comes in, comes in, gets diffracted, and comes in at different angles, more likely than to get total internal reflection. If you put a mirror on the back, you can get the light that hits the back, that mounts back, and you can get multiple passes, and you can get dozens of multiple passes in a good light trapping design. So what you want is, you want it very thick optically, and that will make the short circuit current, or JL, very large. You want it mechanically thin, and the reason you want it mechanically thin is just from this equation. This equation tells you that the smaller W is, the bigger the open circuit voltage will be. And the way to think about that physically is that you have a certain number of electron hole pairs or excess minority carriers. And you want the density of that, so that you have a raw number of those, and they're going to be confined to whatever volume the base is. Well, the density is going to go up as the thickness of the base decreases. And so if the density of X carriers goes up, that means the open circuit voltage is going to go up. So you want a high high excess carrier density number, and that means that you really want to keep things mechanically thin. Now, obviously, these two are competing mechanisms. You can't make it arbitrarily thin, because then the light trapping becomes too difficult to do. But you can, trade off on those two and get some improvement there. Now, the other thing this tells you is that looks like you want a higher doping in the base in order to get a higher open circuit voltage. And that's somewhat true, although you have to be a little bit careful here, because the assumptions that I made to get to this point assumed low-level injection. Our light trapping may actually drive us into high-level injection, which means that I have to go back and rederive the equation for those conditions. And also, lifetime tends to be a fairly severe function of doping in silicon especially, and as the higher the doping is, the lower the lifetime you can get. Plus, there's other recombination mechanisms that will kick in. In silicon, OJ recombination will kick in once you get excess carrier concentrations, somewhere around 10 to the 17th. And again, then you'd have to redo this derivation, making some different assumptions to see what the limitations are. Let's see, but you typically would, and the bases of typical solar cells, silicon solar cells, are 10 to the 16th, 10 to the 17th. And the reason they do that is to get a pretty good high open circuit voltage. There's also another regime which is actually very lowly doped, and that's where you get into high level injection. But again, you would have to derive for that particular condition. Ni squared, you think, well, I can't do much about that, but you can, because while silicon has a particular Ni squared, a wider bandgap material is going to have a lower Ni squared. And so, gallium arsenide has a wider bandgap, it's going to have a lower Ni, and therefore it's going to have a higher open circuit voltage. Now, it suffers, though, from the fact that because it has a higher energy bandgap, it can't absorb as many photons from the solar spectrum as silicon can, because it can only absorb the photons with energy above 1.42 electron volts, whereas silicon can absorb everything from 1.12 electron volts. So there's going to be a trade-off between current and voltage in that particular case. So that's the trade-off with the light current that's mentioned right here. Okay, and just remind you that we assume perfect back surface reflector and essentially an ideal emitter. And then you have to, like I said several times, you have to modify this expression to account for some other recombination mechanisms. But you can do that relatively easily. And it turns out, some cases, for instance, if you were in high level injection and you basically had very low lifetimes, silicon basically radiative lifetime isn't very important because it's indirect bandgap material, but OJ is important. If you had an OJ recombination dominated device, you would actually see a 2/3 out here in front. It would actually have an N factor less than 1. I don't think I've seen that in anything yet, but if you had a really, really efficient silicon solar cell where you would probably see N factors of 2/3 in that device. Okay, so this is going to illustrate some of the points that I mentioned before. So this is, what this plot is the short circuit current, available short circuit current as a function of band gap. So very small band gaps basically can collect the whole spectrum. So there's, and this is a AM 1.5 direct spectrum, if you want to see what this particular spectrum is. So you can get a lot of current, but not very much voltage. So, but as you go up, the current will decrease, and but the band gap and therefore the optic voltage is going to increase. So silicon's right around here, and so silicon, you can probably, if you had perfect light trapping and be able to absorb all the photons in a silicon device, you could get as much as 40 or more milliamps per square centimeter of short circuit current. And gallium arsenide, you can see it's right around here at 1.42. It's under 30 milliamps per square centimeter. So that's the trade-off between voltage and current that I talked about. Now, I guess I'm going to use this right here, right now. But you can see is that, let's say I use silicon, I'm only going to use this part of the of the spectrum. And these higher energy photons I'm probably not using very effectively. Suppose I have a 2 EV photon, I'm almost using only less than half the energy of that photon in the device. So coming up in the talk, we're going to talk about multi-junction PV systems. In other words, where there's going to be 2 different band gaps or 3 different band gaps or 4 different band gaps used simultaneously to get a higher conversion efficiency. But this kind of shows you the trade-off between current and voltage. The other thing is that the leakage current is a key thing. And this is a plot that shows a number of things. So the black line is room temperature, that's 300 K. And this shows how J0, which is proportional to to Ni squared, varies with band gap. And you can see that wide band gap materials have a very low leakage current, whereas low band gap materials have a fairly high leakage current. And of course, these are solar cells are going to be operating not, if we're putting them in a power plant, we're subject to the whims of Mother Nature. And in a day like today outside, they're going to be operating at even at ambient temperature, they're going to be operating at a much higher than room temperature, and they absorb energy as well and heat up just in the sun, so they can get very hot. And you can see what happens as the temperature increases, the leakage current increases, and therefore the voltage goes down. So, and this has become more important, probably the first 20 years we were doing modeling, all the metrics were at room temperature measurements. And so we didn't really worry a lot about what happened, with temperature. Well, we did worry about a lot, but not as much as we're doing today. Now we're talking about deploying these devices, out, in power plants, out in the desert where the temperatures are high, in different places, and the temperature behavior is very, very important. And so this kind of a curve will give you kind of a general idea of where you are. Now, this doesn't mean that all silicon devices are going to be right on this line. This particular line, as I mentioned, are for state-of-the-art devices. So all the devices, let's say take the black line here, although I probably have to revise this since the last PVSC because I think some of these numbers have changed, but this straight line is pretty good representation for all of the best devices irrespective of band gap. But there's plenty of devices that show up all over down here. The poor devices will be higher up on this curve. There's something called the Shockley-Kaiser limit, and it's a line that is just under at room temperature, is actually probably not too far off from where this red line is. And as we get closer, we'll be approaching that Shockley-Kaiser limit with the very best solar cells. But this formula is a pretty good function of making predictions about what's going on with basically where the technology is today and what you might be able to do in terms of producing a solar cell. All right, so I'm going to talk a little bit about, not a lot, but a little bit about fundamental limits of solar cells. And Here's the reference to the paper I mentioned, the Shockley-Kaiser paper, Detailed Balance Limit of Efficiency of PN junction solar cells. And he defines something called an ultimate efficiency. So that would be if you could collect all the current, that's the JSC equals JL, somehow had a perfect fill factor of 1. And the only way to get that is either to have the device operate at absolute 0 or concentrate the sunlight down to infinitely high concentration, and get the open circuit voltage to be equal to the band gap. And again, it pretty much taking the cell operating temperature down to absolute 0 to get that. But it does give you a very good idea of what the potential, how much energy there is available for conversion. You know you're not going to be able to convert all of this, but you should be able to convert, a good fraction of it if you can get, a fill factor as high as possible and open circuit voltage as close to EG as possible. In this particular plot, I've plotted efficiency, and this is for just a single junction solar cell. And there happens to be a peak efficiency for that. And you can see in for this particular spectrum, and I believe again this is the AM 1.5 direct spectrum, it peaks almost exactly where silicon is. So it's somewhat fortunate that silicon is so abundant and so popular material, but also for a single junction gives us the potential, most energy potential. Now this doesn't mean that since I assumed that the band gap or the open circuit voltage is the band gap, this is a little bit misleading. And if you were to correct this curve to account for realistic voltages, you'd actually see a double hump. And it turns out that both silicon and gallium arsenide are very near ideal materials for terrestrial solar cells. Silicon probably wins out for terrestrial applications right now because it's so much cheaper than gallium arsenide is. But neither one of them uses the photons that absorbs completely well. Gallium arsenide lets everything with 1.142 eV and less, it doesn't even use it at all. So that kind of gives you the hint that, well, gee, if I could put another solar cell underneath gallium arsenide had a lower band gap, I would be able to capture some of that energy back. And that's more or less what we're going to be leading into here in a minute. So a fundamental limit is the Carnot limit. If you took a thermodynamics class, and maybe even from your high school physics class, you're probably familiar with the Carnot limit. Refrigeration uses this limit a lot to do its calculation in terms of, instead of the temperature of the solar cell, this would be the temperature inside your refrigerator, and instead of the sun's temperature, you'd be using the room temperature of your house to calculate an efficiency. But we can do much better than a refrigerator can because the sun is quite hot, 5800 K approximately, and a solar cell is approximately 300 K. And so the Carnot, fundamental limit, with the assumptions that we've made is around 95% efficiency. Now we're not even close to that today, obviously. And this doesn't tell you how to do it. It just says this is what might be theoretically possible. Now, there are some more detailed calculations that put the limit closer to 87% as you add more and more junction. I talked about adding one under gallium arsenide to collect that energy, but you can put another one under that. You can put one over gallium arsenide to more efficiently collect those, and you can basically keep stacking and stacking and stacking. And there's been a lot of work looking at what this fundamental limit is. And many of them say that many of those calculations point to an asymptotic efficiency, somewhere around 87%. It varies depending on what exact assumptions they've made. I looked at this a few years ago and I realized that, you probably can't just keep adding junctions. Eventually, there's going to be, if you think about it, every time you add a junction, you're taking away current from the other devices because you can't, there's only so much current available. So if you have an infinite number of junctions, all the devices have essentially zero current, although there's infinite number of infinitesimal currents, but they also simultaneously have an infinitesimal voltage. And if you look at the limit of what that is from a mathematical perspective, it actually will approach zero as you do go to an infinite number of junctions. And if you do the calculation, again, use this simple analytic model to do it, you'll get an efficiency curve that looks something like this. So these different lines are for different solar concentrations. We start at 1 sun and go all the way up to 10,000 suns, which is getting close to the maximum concentration that you could get on Earth, because you can't concentrate the light any more so than it's concentrated on the sun. So you can't get an effective temperature any higher than the effective temperature of the sun's surface. And I've seen numbers ranging from anywhere from 50 to 70,000 suns, probably depending on the assumptions in the calculation. So 10,000 is a pretty good number. I've seen concentrators at 1,000 suns. I haven't seen anything at 10,000 suns yet, at least for solar applications. But you can see that, as you would expect, as you add junctions, the efficiency goes up, but there seems to be some diminishing return. Going from 1 to 2 junctions, there's a big jump. I guess 1 junction is, I don't think it's on the plot. I guess it must have started at 2. But 2 to 3, you get an improvement, 3 to 4, etc. But then you start getting into the fact that you keep diminishing the current, in the sense it's a current voltage product, it tends to flatten out. And it turns out the flat part is somewhere around 55 junctions. Now, no one is even contemplating 55 junction solar PV arrays right now, although there's a company called MCOR in Albuquerque. They're right now working on a 6 junction PV system. So this is kind of a good lead in. So once you have more than 1 junction, you kind of have to change how you look at things a little bit. Fill factor, open circuit voltage, and short circuit current work real well for understanding a single junction. A little bit harder to use those to understand what's going on when you have 2, 3, 4, or 5 junctions. And one of the research projects I'm working on right now is a DARPA-funded project. We're actually looking at a 4 or 5 junction system. And so you can see one of the conceptions of that system is sort of shown here. So you have light coming in of all different colors, have some kind of collecting optics here, and it may be concentrating it as well. And in this particular concept, you have, say, a very wide band gap semiconductor right at the top. And you let the light go through it, and all the energy below its band gap passes through. And then you have basically an optical splitter here. And this is meant to be represented dichroic mirror. Some of the energy is reflected and goes to what we call mid-band gap devices. In this case, there's 2 devices stacked on top of another. And the light that's transmitted through the longer wavelength light goes to another 2-cell stack. And the efficiency, or the output, is going to be, the efficiency is going to be basically the sum of all of the power output of all those different junctions. But it's kind of hard to look at that and try to decide what's going on in terms of, have I made the right choice of junctions and things like that. Maybe not as clear of what's going on. So there's another way to look at things, is to write the system efficiency as this quantity. And you can derive this from first principles, and you can take a look at this paper to see how it's done. But it's a relatively simple expression, and it kind of gives you some insight into some of the difficulties that you might get. So this eta ultimate is what I'd referred to in that previous graph on what Shockley-Kaiser called, if you have a particular set of band gaps and assume that you could get the open circuit voltage from each of those band gaps, that would be the ultimate efficiency that you could get for that set of band gaps. The photon efficiency here is basically making sure that every photon goes to the right band gap semiconductor. So ideally, you wouldn't send a 2 EV photon to the silicon device. Silicon device would be able to use it, but it wouldn't be able to use it as efficiently as, let's say, a 1.9 EV device. So how well you're able to do that is the photon efficiency. In a real system, you have to connect all these things. You got 5 junctions. You've got to be able to get that power into, let's say, an electrical inverter or something. There's going to be some electrical losses associated with that, and so that's what the A to IC interconnect efficiency is. And then there's a term that looks a little bit like our standard figures of merit. There's this weighting factor here, which is basically just a ratio of how much energy each of the PV devices is seeing. The sum of these betas is equal to 1, but other than that, it's really not the key thing to look at right here. Fill factor is the same as our fill factor as you already know, but instead of looking at open circuit voltage, we look at the voltage efficiency, which is the ratio of the open circuit voltage to the band gap. So its efficiency would be 1 if we could somehow get to the band gap voltage. And when you look at this equation and stick in typical numbers, what sticks out at you is that this ratio is much smaller. This collection efficiency is very close to 1. The voltage efficiency is nowhere near 1. I mean, in fact, for low band gap devices, it's quite small. And so this is definitely a key area of research on how to get the open circuit voltage, as high as you can. Again, collection efficiency, which is typically 1, and it'd be great if we could convert half the energy in the solar spectrum into electricity. But if you take a look and say this is really the product in some sense of 6 terms: the ultimate efficiency, photon efficiency, interconnect efficiency, fill factor, voltage efficiency, and collection efficiency. If we had just one junction, it would just be those 6 terms. And now you got 6 numbers multiplied together. In order to get 50%, you have to have about 90% efficiency in each of those steps. Well, the ultimate efficiency for a single band gap is not there. It's roughly a half. So you have to go to multiple junctions in order to get this number even close to 89. And it takes a lot of junctions to get up to that high. And the other key thing that jumps out at you is that the voltage efficiency is very low. All right, so I'm going to sort of shift gears right now and get back to basically where my roots came from, and actually Professor Lundstrom's too. My PhD thesis was on detailed numerical simulation, sort of following in Professor Lundstrom's footsteps. He did a one-dimensional device simulator, and I did a 2-dimensional device simulator. And then these programs have evolved over time here. But the detailed numerical simulation, is based on much more rigorous device physics. I think Professor Lundstrom, I saw his slides, and I think he showed you the semiconductor equation, Poisson's equation, the continuity equations. So we're going to basically solve those equations with making as few simplifying assumptions as possible, which means we're going to need the computer to do that. And what it does is, if you can do that, then you can basically generate everything that we did with the analytic models, but without having to make the same simplifying assumptions. We can generate terminal characteristics, and that's sort of like I mentioned before, sort of the predictive capability of it, and then also do diagnostic capability, because not only can we generate the external terminal characteristics, we can also take a look at what's going on inside the device. And Professor Lundstrom mentioned that he showed you lots and lots of pictures of what was going on inside. And that's probably the main difference between, or at least one of the most powerful features of detailed numerical simulation is it's like taking a microscope and looking inside the device. But it also allows you, there's still a lot to be said for analytic models because they're simple to use and give you a little bit more intuition of what's going on. But this is a convenient way to make sure that the assumptions that you've made are really valid. So before I get talking more about what's under the hood in terms of detailed numerical simulation, to kind of give you a very brief, not comprehensive overview of solar cell simulation at Purdue. And I already mentioned that Professor Lundstrom started with SCAP-1D, was his program back in about 1979. We both had the same major professor, Dick Schwartz, and I followed on a couple years later with the 2D simulator, SCAP-2D, very original title for the name. And then Professor Lundstrom actually kept working with modeling for a while and he had students working in the mid-'80s on a program called PUFs, and that was mainly for 3-5 heterostructures. At about that same time, Dick Schwartz and I started looking at amorphous silicon solar cells, and we created a program, TFS, it's called Thin Film Semiconductor Simulation Program, and that program is probably the main source of where ADEPT has been derived from. But it started out trying to do amorphous silicon solar cells. And we had to include a lot more device physics to do the amorphous silicon, and that's when we realized that if you write the program right so that it can handle lots of different materials, you don't have to write a new program every time you look at a new material. And so you can see here we look, and yes, I'm not going to go through the whole list, but you can see there's just a number of materials that we've been looking at. There we go. And ADEPT 2.0, I think it's called, is on the NanoHub. That's the original Fortran version of it. We have multiple, and it just does one-dimensional simulation. There's multiple C versions of the code, both 1D, 2D, and even 3D. And actually, it's a single code that can do 1D, 2D, and 3D simultaneously, and that allows you the benefit of sort of using some of the same code over, especially for device models, without having to write things. And I'd say relatively recently, MATLAB, which is basically written in C, has become sophisticated enough and fast enough that I'm right now working to basically convert the code into a MATLAB environment, and that'll make it a lot more customizable by an individual user, because it'll just be a MATLAB toolbox. You'll call a function, and then you can manipulate the results in any way that you want and not be at the mercy of whatever the designer of the particular software that you're using decided was important to look at in terms of analysis. So when you do detailed numerical simulation, you got to give us some inputs. And I was going to put this on a slide, but I forgot to do it. And this is sort of, this is sort of key. I remember the first programming class I took, almost the first day of class, the instructor said, remember this acronym, GIGO, garbage in, garbage out. The computer is going to do exactly what you tell it to do. And if you tell it wrong, it's going to give you exactly the wrong answer. It'll give you the answer that's right for the input that you got, but it may not be what you thought you had told it. So never, even though I do numerical simulation all the time, I don't trust the output at all until I've done some sort of sanity check on the result and tested it. And that's the key thing. Just because someone wrote a program and it spits out a result doesn't mean it's right. And remember, you're also giving it inputs, and you may have given it some wrong inputs. And I know some of our students have run into that very fact. They'll get some very strange results, and they'll either discover that it's something that they did in terms of the inputs aren't behaving the way that they thought they were, or there's some honest questions about what assumptions the program is making and whether they're valid or not. But you'll give it the structure of the device. You got to set up basically the geometry of the device. You got to describe all the materials, all the material properties, because those are all inputs to the program. And then you got to tell it what operating condition that you're at. So the light that's on it, the operating temperature, whether it's DC, small signal, transient, all sorts of things like that. And you've already probably seen, I don't know if Professional Electrician showed you a typical input, but ADEPT basically doesn't use a GUI, although you could write a GUI to generate this type of an input file. But it's basically just a simple set of dictates that sort of describe the device and the material, the properties of each layer in the device or each region in the device. Outputs are probably the thing that everyone is mainly most interested in, and the Professional Instrument showed you lots and lots of pictures of that. But once you've got the solution, then you can look at anything you want to try to understand what's going on. And as I mentioned a couple times before, the terminal characteristics are sort of like a predictive, you use it maybe as predictive, and then when you look inside the device, that's sort of a diagnostic use of the code. And I've just got a few plots that sort of illustrate that. This is for a 3-junction. We talked about multiple junctions, and so These are the output characteristics, IV characteristic for 3 different junctions generated by adept simulations. And then if they're connected in series, you would get a total IV characteristic that looked like this. You notice that the short circuit current is limited by the short circuit current of the lowest one, which happens to be the green curve in this particular case. Since they're series connected, you're always limited by the lowest current. You can look internally to the device. What I find the most useful plot is looking at the recombination in the device, because that tells you an awful lot about what's going on. Just sort of an example right here, you see actually you see 2 spikes in the recombination rate, right here and right here. And you might say, in absence of anything else, say that, gee, something really bad is going on there in terms of recombination, and this is something I really need to fix. But you really need to look at something else as well, which is how much does that recombination contribute to the total recombination going on in the device, which is the dashed line here. And you'll notice that as that line goes through these points, it barely even budges, which means these spikes in recombination, which look like they're very important, aren't important at all. And actually what this says is that because this dashed line starts out almost at the surface, something very close to the front surface of this device is creating a lot of recombination. And at the back, looks like 15% of recombination is just occurring right at the back contact. And that these spikes in recombination really aren't important at all, because they're not adding anything to the recombination current. Okay, so now we're going to get to under the hood, the under hood part. So this is the semiconductor equation. So we have Poisson's equation, the continuity equations, and then the transport equations for this. And so it's relatively 3 partial differential equations with some auxiliary equations for the currents. And the operating conditions, material properties, and other physics are in the boundary conditions, and the parameters that appear throughout. There's temperature, dielectric constant, traps, which includes doping, generation rate, recombination rates, mobilities. VP and VN are called band parameters, and they account for the fact that the band gap may not be constant with position. If you may have a heterostructure, and those properties are captured in the band parameters. So all the physics really is in these things, and this in terms of the specific physics are in these things. So we have these differential equations, which we can't solve analytically without making a lot of simplifying assumptions, that's where the minority carrier diffusion came from. But we don't want to do that. We want to try to solve these as exactly as possible. So the first step to do this numerically is to transform the differential equations into difference equations. And that means creating a spatial grid, either in 1D, 2D, or 3D, and changing the derivatives into differences. So think back to the fundamental definition of the derivative, which is delta y over delta x, and have those approach 0. Well, we're just going to have those small. We're going to approximate the derivative essentially by using differences. And you can go through and do that. And so you'll create a difference equation for every point in the grid when you do that. Now, what results is a very large set of nonlinear difference equations. Typically in a 1D simulation, you'll use 250, 1,000 mesh points. So that means you have 250 times 3, because there's 3 separate equations at each mesh point. So 750, 1,000, or 3,000 equations. And unfortunately, they're nonlinear, which means you can't just make a matrix and solve for the solution. But I'm sure you're all familiar with Newton's method for solving find the root of a nonlinear equation. So you can apply a generalized Newton method to solving this large system of nonlinear equations and iterate to find its zero or its solution essentially. And that's what's represented here in this equation, where K is representing an iteration number. And I think for a typical number for that is probably 10 to 20 iterations is probably what you can typically do. Sometimes even fewer than that. Some complex materials may take a couple hundred iterations, but typically a single crystalline is pretty well behaved and will converge relatively quickly. And so the programs can run very quickly. I've had my grad students run literally hundreds of thousands of simulations overnight. So obviously it's got to be pretty quick to be able to do that. And what we'll solve for are the carrier concentrations and the electrostatic potential at every point in the device. Now, you think, well, gee, if I have 1,000 nodes, that's 3,000 equations. That's a matrix that's 3,000 by 3,000. Fortunately, though, it's very sparse. And so this is a representation of the sparsity of that matrix. And in fact, in one dimension, it's block tridiagonal, so that, there's 9 times, see, this is 3,000 by 3,000, so this is 1,000 nodes with 3 equations at each node. That's 9 times 10 to the 6th elements in the matrix, so 9 million elements, but only 33,000 of them are non-zero. And also, since it's banded, I only have to store the non-zero ones, and it's very efficient to solve that equation. 2D, even bigger equation, let's suppose that you had 100 by 100 by 100 mesh, times 3 equations per mesh, that's 30,000 by 30,000, so that's 9 times 10 to the 8 elements. 500,000 of them are non-zero, but that's still a small fraction of 1% are non-zero, so sparse matrix. Now, we used to spend a lot of time using with meshes to solve that. MATLAB now almost handles this automatically for you. You just use sparse matrix, and it'll figure out the best way to invert it and solve it for you. So I used to spend a lot of time worrying about that. I spend almost zero time worrying about that anymore. I just don't store all 9 billion or 90 billion, 9/10 of a billion elements. And that's basically it. So let me just kind of go through this under the hood sort of thing for you. So just one last time, just don't lose track of the equations that you're solving, when you're using the computer program, and don't think of it as magic. Adept isn't magic, Centaurus isn't magic, SCAPS isn't magic, PC1D isn't magic. They all basically solve the same set of equations, and they all solve them pretty much the same way, with slight variations, but fundamentally they're the same concept. And the key thing is the assumptions that go into it. So, they have a set of equations, they'll discretize them, solve them with some type of Newton-type method for the nonlinear part, and then plot the results and give you some, they'll give you some control over the inputs, which is good and bad. If you're not sure what to do, you can make some very bad choices for what the inputs should be. But then again, relying on what they think the best numbers are can lead to some problems as well. So when you think about that, you should now have a basic idea of what goes on under the hood in any type of simulation program. But the main thing I want you to come out of here is with question every result, make sure it makes sense to you. Because until it makes sense to you, you really can't believe it, because these are things that are very hard to test without having some intuition involved in terms of, yes, that makes sense in terms of how it behaves. All right, so any questions?
For a multi-junction cell, it seems like just putting them in series is, you said something about if the series, if the short circuit currents don't match, then you have problems. I would see that could cause some cells to be sort of put into forward bias. So is that part of the optimization? Well,
yeah. Picking the band gap, so that's perfect. But there's debate about that. Many of the cell manufacturers, they're much simpler to make. A lot of times they'll be built in a stack, all basically monolithic stack. And so it's much easier not to have to worry about getting extra contacts put in there, so they'll want to make them in series. But then you have to optimize to pick exactly the right band gaps. And let me go back to this graph. In this particular graph, I show number of junctions, but in each case, the band gaps of those junctions were picked to be the ideal band gaps to give you the maximum efficiency for that number of junctions. So it is very sensitive. And it turns out that if you put them in series, it gets very sensitive to the operating condition because you got to be exactly matched. And if you look at the efficiency curves, like just for 2 junctions, it's a very steep curve. Here's you're exactly matched. If you change, let's say, the spectrum of the light just a little bit either way, you fall off of that. Whereas if they're electrically independent, it's a much flatter curve. So in fact, the meeting that I came back at, there was 2 camps there. One that believed that we can pick the band gaps, it's not going to be sensitive enough that we worry about it. Another camp that really insisted that you really should have multiple terminals. Now, the people that have to worry about all of those electrical lines really don't want to have to worry about all that because it makes the manufacturing a lot more complex. And so, actually, I've had graduate students look at, and other people have looked at this as well, what's the sensitivity to exact match of the spectrum? How much can you get away with by putting them in series with one another? But the key thing is to match that band gap. And not only match the band gap, but make sure you're matched it at what the anticipated operating temperature is, because it's also sensitive to that, because band gap changes with temperature. As the temperature goes up, the band gap goes down. And so your matching changes with temperature as well. So you have to anticipate what your operating temperature is going to be, but clearly that's not going to be a constant. In the winter, especially in Indiana, it's going to be much lower than it would be in the summertime.
Is there any advantage to doing a doping gradient for the backside field, or has that been tried?
Yeah, I mean, there can be. In thin film materials, actually, they do try to do that, partly because they have, the advantage there comes from if you have trouble getting the base lifetime high enough. And so that, the diffusion length is shorter or on the order of the thickness of the device, then that built-in gradient of the field of the doping can help you enhance collection. But if you have very long lifetime, then you're probably not going to see much benefit from it. So again, it depends on the particular situation.
Since the electron absorb a photon and if the photon energy is larger than band gap, and the electron will dissipate that portion of energy to the whole device. So is the self-heating problem very important?
Oh, very important. So you really need to, especially in concentrator devices where you're, instead of just having one, heat sinking is very important. I mean, that's the basic answer. And with concentration, it becomes even more and more important to keep you want to basically be able to pull the heat out of the excess heat out of it as fast as possible.
Sort of like a follow-up to that, actually. Can you get anything out of spectrally concentrating the light?
What do you mean by spectrally concentrating?
Like doing, some sort of fluorescent molecule that will down convert to make the spectrum that you're grabbing with the gallium arsenide more like.
Yeah, some people are looking at some of those things so that you somehow convert one photon into 2 so you can maybe use it more effectively, or conversely combine 2 low energy photons together to get a higher energy photon together.
But not even something so complicated. Is that just something where you maybe take a 1.1 eV photon, turn it into 1 EV photon, so that 0.1 EV is dissipated in some optical piece instead of something you need to heat sink really well. I'm just wondering if you can change where the heat dissipation is enough to win.
I don't know. I guess it would probably depend on the efficiency of the process to do that. Yeah. But yeah, that's an interesting idea, actually.
I noticed that you're primarily dealing with inorganics. Have you ever looked at these simulations for organic compounds?
Only very little with Professor Olam. I know he's doing some simulations. So I'm not sure I could, but ask if you have a particular question, I'll do my best to
I
answer.
thought there was any advantage to doing that if you had ever simulated that, or is there any advantage of using organics versus inorganic?
I don't think we can use, or at least right now, I'm not sure you can use simulations to decide whether organics are better than inorganics. You can certainly use simulations to help understand what's going on with organic devices to see, how to make them better. Right now, they're not competitive efficiency-wise with inorganic materials, but modeling can certainly help improve that situation and do things. But I'm not sure it's going to tell you that inorganic is better than organic, because there's so many things that, in terms of the simulation, that aren't part of that equation. Especially the cost. The most important thing, in whether technology is going to be win or not, is its cost, and how much does the electricity that comes out of it cost you? And detailed numerical simulations will contribute to understanding of that, but they're not going to give you the answer, because they're really going to be the economic assumptions that are going to dictate that.
I think we have a whole lecture on organics, right?
Yeah, tomorrow, the last lecture.
We saved the best for last.
Yeah, you have lots of color.
When you're solving the drift diffusion equation, in the boundary as the interface, you use the law of the junction.
Are you talking about detailed numerical modeling? No. In detailed numerical modeling, no. All we solve for is basically recombination and charge things at the interfaces. Law of the junction actually comes naturally out of the solution of the detailed equations.
Okay, so the boundary condition for your model is just the boundary condition just comes from the contact
Contacts in the surfaces, yes.
and the surface.
Yeah.
The interface you don't.
No. Those are interfaces. You can treat those as actually bulk properties. So they're not really treated as boundary conditions.
Mm-hmm. But at the beginning of your slides, some slides show the law of the junction.
Oh, sure, but that was for solving the minority carrier diffusion equation. And that's a simpler analytic model where then you have to apply that. But when you do the full detailed model, you don't have to do that any longer.
Thank you.
You're welcome.
Is there any other question?
If you have a really great lifetime in the base region, such that you're in the short diet regime, is it to your advantage to make the base longer at that point?
No. In fact, if you go back to this equation that we showed earlier, that's been thrown away. It's exactly the opposite. Your advantage is to make it, it's in the denominator, so the advantage is to make it narrower. Now, that's assuming that you can trap all the photons and collect and basically get generation from all the photons in there. But then the reason that that you want to make it smaller is that it's a density. The open circuit voltage is related to the density of excess carriers. And so if they're confined to a smaller region and it's the same number of excess carriers, the density is going to be higher. If the density is higher, then the voltage is going to be higher.
Thank you.
Okay, let's thank Professor Gray.